recently as well for the invitation to give these lectures. So I will talk mainly about point-wise convergence theorems in analysis and ergodic theory. And first, so the plan is as follows. So I would like to start with convincing you that maximal operators are very efficient in these problems. So very nice tool. I will define very basic operators like hard-limited maximal operator and so on. So I will start from very basic things. Then I will give some examples and also some examples in which maximal operators are not so efficient. So later on, I will define more sophisticated tools like variational oscillation and lambda semi-norms, and show that they are much more efficient, but the disadvantage is that they are much harder to build. All right, and later on, I will show Levin inequality, that is variational estimate for martingales. Here I focus on quite general martingales, but not general martingales. And at the end, I would like to give a proof. I think that if time permits, it will be more or less complete proof of Bourgain's theorem for ergodic averages along squares. So I want to prove that the corresponding maximal function or variational estimate holds for L2 functions. Okay, so that's more or less the plan for this week. So today we start with maximal operators.
Tomasz, you should point at the laptop, not at the slides, right?
All right. So our situation is as follows. So we have a measure space X mu. We assume that mu is a sigma finite measure. Sometimes we will assume that mu is finite, but in most of the cases, sigma clearly will be enough. We fix P. P is between 1 and infinity. In some cases, we will exclude P equal to 1, but at the very beginning, we will include P equal to 1 as well. And we have also some family of linear operators Tn, which are defined on LP space. Okay, and the question we want to ask is if this sequence converges almost everywhere for any LP function. Okay, and let's notice that the first observation is that if it indeed converges to some function almost everywhere, it means that the corresponding maximal operator, which I know by T star, is bounded, right? Because if the sequence is convergent, then it is bounded, and the maximal operator is bounded almost everywhere. All right. So first of all, I would like to show you the following theorem, which is called Banach principle, and which more or less tells us that once we know that the sequence converges, or even if we just know that the maximal operator is finite almost everywhere, then in fact we have some quantitative information about the distribution of the maximal operator. So the assumptions are as follows. So we have a measure mu. We assume that it is finite, and we need to assume that. If we assume that it is infinite, then we will find easily a counterexample to this theorem. Then we assume that TNF are measurable and finite almost everywhere. So this is a very mild assumption. And almost the last thing we assume is that TNF are continuously measured in the sense that if we, for each n, if we have a sequence which converges to some function in LP, then Tn at f converges in measure. Okay, so this is convergence in measure. Okay, you may think that f is just equal to 0 because we are dealing with differences here. Okay, so n is fixed, and for every sequence which converges to f in LP, we know that Tn at Fn converges to Tn f in measure. Okay, so this is a very mild assumption, and the last assumption is that the maximal operator is finite. So in particular, if our sequence converges, then the maximal operator is finite. All right, and in such a situation, this theorem tells us that there exists a function C lambda, which is decreasing and which tends to 0 as lambda tends to infinity, and such that the distribution of this level set for the maximal operator is uniformly bounded by C lambda for any LP function. Okay, so this is what this principle tells us. Later on, we will get to know that, in fact, if we assume something more about the function C lambda, because here we almost know nothing about this function, then we can somehow reverse this theorem in the sense that this kind of estimates more or less gives us convergence of the sequence TNF, almost everything. All right, so let us look at the proof of this Banach principle. So our aim is to show that we have this estimate and also that C lambda tends to 0 as lambda tends to infinity. So first of all, we terminate our maximal operator. So we define terminated maximal operator when we take the supremum up to level capital N. And this is just a technical assumption. So here we want to know that this maximal operator is continuous in measure. So this is a maximum of N operators which are continuous in measure. And then it's quite natural to define the function C lambda as follows, because first of all, this estimate by homogeneity of the maximal operator, we can move this LP norm to the left-hand side, and we may think that function f has norm equal to 1. So this is quite natural to define the function C lambda as the supremum of the left-hand side when we consider all LP functions with norm 1, right? So then it's clear that this function decreases, because if lambda is larger, then these sets are smaller, so we have smaller measure. So the only thing we need to show is that when lambda tends to infinity, it goes to 0. Okay, and how we do that? So first we write down LP space as a sum of this sets. So we can do that because we assume, so this is the only point we use that the measure mu is finite. So if we take a limit when n tends to infinity, then the limit of those measures tends to the measure of the set that the maximal operator is infinite. And by the assumption, we know that this is 0, right? So for any LP function, we can find n such that the measure is smaller than epsilon. And now the whole point is that we want to show that each such set is closed. And this will be more or less the end of the proof, because we will be able to use Mayer's category theorem. All right, so how to do that? So if we knew that the maximal operator is continuous in measure, then we will be done. But we do not know that. So for technical reason, we introduce this truncated maximal operator because we know that they are continuous in measure, and we can write down this identity here. Okay, so here we do not use the fact that mu is finite. We just use the fact that any measure is continuous. Okay, so in other words, if the maximal operator is larger than n, Sorry, it's quite easy because the measure of this set is the limit of the measure of those sets. So if all of them are smaller or equal to epsilon, then the limit is smaller as well, and those sets are smaller, so we can easily conclude this identity. And here the point is that using the fact that this truncated maximum operator is continuously measured, one can easily see that those sets are closed. And since they are closed, and we take the intersection of closed sets, then we see that the left-hand side is closed as well. Okay, and this left-hand side is just the term which is used here. So in other words, we were able to write down the LP space as a comparable sum of closed spaces. Okay, and now we can use Bayes category theorem, which tells us that any complete metric space cannot be written as a countable sum of lower than sets. So this means that at least one of those sets has a non-empty interval. Okay, so this is the main thing here. By the way, let me know if you have any questions. All right, so we know that for some n, this set on the right-hand side here has a non-empty interior. So equivalently, we may think that there is f0 and delta such that the closed ball centered at f0 and with radius delta is contained in that set, which means that for any G with norm at most 1, we have this estimate. Okay, so this is exactly the same that closed ball centered at f0 and with radius delta is contained in one of those sets. And now we can use the triangle inequality. So we may, for any LP function with norm 1, we can estimate this maximal function by the sum of these two maximal functions. And now we can use this fact. So once again, using the triangle inequality, so here we put 2n. So by triangle inequality, it means that one of the function is greater than n, or the second one is greater than n. And using this identity, once with g and the second time with g equal to 0, which is allowed because we allow all functions with norm at most 1, we can conclude that the level set for this function is at most equal to epsilon. Okay, and if we look at the definition of C lambda, it means that it is a supremum over all functions g with norm 1. So if we move this delta to the right-hand side, and if we take the supremum over all functions g with norm 1, then what we get on the left-hand side is a definition of C at point 2n divided by delta, and we know that this is at most 2 epsilon. Right? So we found a point at which function C is less than 2 epsilon, so it means that that function C tends to 0 as lambda tends. Okay, so we have this this result, which tells us that having maximal, more or less just assuming that the maximal operator is finite, we can conclude that it satisfies some quantitative estimate. Okay, and in fact, this result can be upgraded if we assume some structure about space X, as well as when we assume some structure on operators Tn. So Stein in 60s was able to upgrade this estimate to the estimate of this type, which means that we take C lambda equal to lambda to minus p. If we assume that we are in the case of compact abelian groups, mu is a Haar measure, and also operators Tn are not random in the sense that they are very particular operators, which convolutes with translations. Okay, and in such generality, this works only for P between 1 and 2, and this is sharp in the sense that in this generality, it's possible to find counterexamples for P greater than 2. Okay, but on the other hand, we can. It's possible. It was observed later on that if we give even more structure, then the result works for P greater than 2 as well. Okay. All right, and the second remark is that in fact before this result, Kolmogorov observed that for the truncated Hilbert transforms, the pointwise convergence for truncated Hilbert transforms is equivalent to weak type 1,1. That is this estimate for P equal to 1. Okay, so first he was able to observe that this is equivalent, and then in fact he proved this estimate for P equal to 1, and he was able to prove pointwise convergence truncated.
Excuse me. Yeah, in the previous proof, why you couldn't send P for P from infinity last year?
Why I cannot include here P greater than 2?
Yeah, in the previous result of the why.
Yeah, I was able to prove it for an P smaller than infinity.
But why not for an infinity?
Okay, that's a good question. It's a good question. Maybe it's possible. Okay, I need to think later on. We can see how that. Now I do not see why I cannot do that. Yeah, I don't know. All right. So this was somehow an introduction, and now I would like to introduce some notation. So I would like to look at this problem from the other point of view. So we want to have some estimate for the maximum operator, and we want to conclude that we have pointwise convergence. Okay, so first of all, for NLP, here at some point I will need P smaller than 1 as well. So I will introduce everything in a such generality. So here we have a linear operator or sublinear operator T, and we define weak type PP estimate to be an estimate of this type. Okay, so this is exactly what appears in Banach principle, but with function C lambda equal to 1 over lambda P. Okay, and so the trivial example of an operator which satisfies this weak type PP is identity operator. So if we put TF equal to F, then by the monotonicity of the integral, we get this estimate. This also shows that the space of functions which satisfy more or less this estimate with TF equal to F is larger than the LP space. So by LP infinity, I denote weak space LP. And now I consider operators Tt and continuous time, but it doesn't matter because you can still think that T is just a natural number. And I defined the associated maximal operator to be the supremum over all operators Tt. And we have this very nice lemma, which is very useful in applications, and it tells us that if P is between 1 and infinity, and if we assume that the maximal operator is of weak type PP, then the convergence holds for a closed subspace of LP functions. Okay, so the subspace for which the convergence holds at infinity or at 0 is closed in LP. And this is quite important because if for other reasons we know that this space is also dense in LP, then we know that the convergence holds for all LP functions. Okay, so that's a very important observation. And I will show you, well, here is the reasoning which justifies this lemma. It is quite simple. So what we do is we take an LP functions and a sequence Fn which converges to F, and we assume that for Fn we have convergence. So in particular, we know that TTFN is a Cauchy sequence, and what suffices to show is that the sequence TTF is also a Cauchy sequence. Right, so it suffices to show that for almost all x's, the following limit superior is equal to 0. Okay, and how to do that? So we first want to see if it is possible that this limit superior is greater than some positive constant lambda. So what we do here in the first line is we artificially add TTFN, because we already know that the limit superior for Fn is equal to 0 because we have convergence. And then we use the fact that this limit superior is bounded by 2 times the maximum function of the difference. Okay, so then using the weak type PP, we get this estimate, and if we let n goes to infinity, then we have 0 on the right hand side, and the left hand side does not depend on n, so it is equal to 0. Okay, so we know that it's not possible to have limit superior to be greater than lambda, and if we choose the sequence which tends to 0, then we see that it's not possible that this limit superior is positive. Okay, so this means that for almost all points from x, we have we know that the sequence TTF converges almost everywhere. All right, and this leads us to what I've already mentioned, a very nice tool which allows us to deal with a pointwise convergence without appealing to sets of measure 0. Because observe that if you have a particular problem and you want to show that some sequence converges to some function almost everywhere, and this convergence is not for all x's, then the problem is how to find this set of measure 0, right? And this nice corollary allows us to omit this discussion. So what we have here, we have a two-step procedure that in order to prove pointwise convergence for the sequence TTF, it suffices to check 2 things. So the first one is some quantitative information, that is that the corresponding maximal operator is of weak type PP. And the second thing is that we have convergence on a dense subspace of LP. Okay, and in practice, the first point is usually much harder to show than the convergence on the dense class. However, there are some cases in which finding a dense class is a very challenging problem, and I will give you some examples later on. Okay. All right, so let us look now on the examples in which we can use this strategy. So the first example is very classical. So we want to prove the Lebesgue differentiation theorem, which is written here. So B is Euclidean ball. So we take the averages along the Euclidean balls, and we want to show that for unknown functions, these averages converge to f of x. I stated this for unknown functions, but the problem is local, so in fact it works for unknown local functions. So here, the dense class is quite natural for continuous functions. We know that this convergence happens. So what is sufficient to show is that the corresponding maximal operator, which is in this case called Hartley maximal operator, is bounded is of weak type 1. Okay. The second example is the famous Carlson theorem. So we take truncated Fourier integrals, and we want to prove that they converges back to the function f. And this is a very did result proved by Harrison in 1966. It's probably one of the best results in harmonic analysis. So here it's not hard to show that this convergence holds for Schwarz class. It's quite immediate. But the challenge is to prove that the corresponding maximal operator, in this case it is called Harrison maximal operator, is of weak type 2. All right, so it was in fact how Harrison did it. So he proved that this operator is of weak type 2. And later on, this result was extended by hand. So in fact, this maximal operator is of weak type PP for every P, and by the interpolation, it's in fact of strong. So it is just modeled over to be fine. All right. Yes, and the last example in which I would like to focus a little bit more is the Berkhoff's ergodic theorem. So in order to state this theorem, I need to introduce some notation. Okay? And later on, we will build some more complicated examples based on this. Based on this theorem. All right. So first of all, we need to introduce some notation. So I would like to consider this quadruped, and this is called the measure preserving system. Is if the first triple is sigma finite measure space, and the last thing here is a measurable mapping from X to X, which preserves the measure. That is the measure of the preimage of any measurable set as the measure, which is equal to the measure of the original set E. And here we have some examples of such systems. So the first system is the most important one from my point of view, because in some sense, as we will see later on, this is some sort of universal system. So another system, in some sense, can be reduced to this system. So here we have integers, we have counting measure, and the transformation is just a shift. Here I choose shift to the right, but as well you can consider shift to the left. Okay. The second example is a torus with a rotation map. So as it is written here, I consider torus as an interval 0, 1, and I identify 0 with 1. And then the measure, of course, is a Lebesgue measure restricted to this interval, and the transformation is just adding over the 1. And this is called rotational system because, as well, we can think that the torus is a one-dimensional circle, and then this transformation is just rotating by the angle, which is 2 pi alpha. Okay. And the last example, which is quite nice, it is called doubling system. So we have torus, we have Lebesgue measure, but now the transformation is 2x modulo 1. And why is it so nice? Because this transformation is it's clearly not a bijection, and if you look at first, you may think that there is no chance that it preserves the measure, right? Because the equation is 2. But if you look at it more carefully and take into account that we add modulo 1, then it turns out that it preserves the measure. Okay? And that's a very nice example of a measure preserving transformation. All right, so having this setup, we can define Hopman operator, which is an operator from LP to LP, and which is given just by composition with a transformation T. Okay, so Tfx is Fx Tx. Okay, and very important observation here is that this operator is isometric on LP. And this is a very simple consequence of the fact that T preserves the measures. So if you want to prove that, then it suffices to observe that this is just a definition for simple functions and then approximate. But all right, later on, I will mention that in fact this observation was not done at the very beginning, and this made that the original proof of the Berkov theorem was much more complicated than the versions which I will show you. So having a measure preserving system, we can define averages along the trajectory of the point x. So here we first take tx, then t squared x, t to the power 3x, and so on, and we take the average of these values. And Berkov theorem from 30s tells us that if we take any LP function, here we put p equal to 1, which won't be the case later on, when we will consider more complicated averages, that is, averages not with respect to a linear trajectory, but with polynomial trajectories, then we need to exclude p equal to 1. So this theorem tells us that these averages converges almost everywhere for any functions. There is also a version with convergence in LP, which is a result also from 30s of von Neumann. However, from our proof, it will be clear that pointwise convergence is something which is hard, in the sense that having pointwise convergence plus having LP boundedness of the maximal operator, we can easily conclude convergence in LP or P greater than 1. All right, so we have our two-step procedure. So the first step is to prove that the corresponding maximal operator is bounded to the P, and this is for P greater than 1. For P equal to 1, one needs to show the corresponding weak type 1. That will focus, well, in fact, later on we'll focus on P equal to 1 because, yeah, I will mention that later on, but what we will be able to do is we'll be able to transfer this abstract maximal estimate to the case of integer shift systems. So this is to consider Z with shift operator, and this reduces in fact to the classical hard-limited maximal operator. And the second step is to prove pointwise convergence for a dense class of functions in LP. So we will start from the second point. So here it's not hard, in fact, to find a dense class. So first we consider the subspace IT, which consists of eigenfunctions of T related to eigenvalue 1. And for these functions, it's well, pointwise convergence is trivial, right? Because the average is just equal to F, because each this term is equal to F. So there is nothing to do. Then we consider JT, which are of this shape. So this is Tj minus J. And the technical assumption is that we additionally assume that G is uniformly bounded. Then we use telescoping argument in the sense that if we consider this sum, then almost all terms cancel out. We just have two terms. The first term from capital N and the second term from N equal to 1. So the numerator is bounded by 2 times infinity norm of G. So when we take N to infinity, then we get 0. So here we have convergence to 0. Right? So the last thing to do is to show that this sum of those two subspaces is dense in LP. Because it's dense in L2, because once it is dense in L2, we will have convergence for L2 functions, and since they are dense in LP, then we will have class of LP, and we can conclude the pointwise convergence. All right, so So the proof is not so hard. We want to prove that the orthogonal complement of JT is IT. All right, and to do that, we first observe that orthogonal complement to this space is exactly the same as the orthogonal complement to a similar space when we threw away the assumption that G is in a field. And then what we do is we just use the definition. So being to the orthogonal complement means that these inner products are equal to 0 for all two functions. Then what we do is we move this T to the left-hand side, so we have adjoint operator. And then if this identity holds for any L2 function G, which means that T star F is equal to F. And the only thing to do is to prove that this identity is equivalent to the fact that TF is equal to F. And to do that, we can use a quite general fact about contractions. So if we have a Hilbert space and a linear operator, which is a contraction, which means that the norm of this operator is smaller than 1, then being an eigen function with eigenvalue 1 for T star is the same as being eigen function with eigenvalue 1 for T. Okay, so this is, well, in fact, I would like to show you the proof of this result because it's very easy. So the first observation is that it is symmetric. Those the fact that the norm of T is smaller than 1 is exactly the same as T star is smaller than 1. So it suffices to just show one implication. So what we do here is we assume that T star X is equal to X, and we want to show exactly the same for T. So we write down the square of the norm of the difference. So then we use inner product, we write it down as here, and now we are moving T to the right-hand side. So here we get X, T star X. T star X is just X. So from both terms, this one and that one, we obtain minus X squared. So at the end, we get Tx squared minus X squared plus X squared. So at the end, we get this one. And since T is a contraction, this is non-positive. All right, so this means that Tx is equal to X. And this concludes the proof that the sum of those two spaces is density. Okay, so this is a very nice argument. And the remark is that this space is not always closed. So in fact, this space here is dense, but it is not really. All right, so we have convergence for a dense class. So now we have in fact the first step. So we want to prove that the corresponding maximal operator is bounded on OP. All right, so we want to prove this one. All right, and how does it look like for the special case? So when we consider shift integer system, then our averages as written as here, because the transformation is just moving to the right, it's shift to the right. So if we apply this n times, then we move by n to the right. And we see that this operator is quite similar to the ability maximum operators. If we consider a discrete version, this is almost amplitude. Well, the average which appears in the amplitude maximum operator. The difference is that this operator is one-sided. That's not like a change in the proof. But what I want to do is to show that in fact this abstract estimate, because here we are in a general situation of measure preserving systems, can be reduced to something which is totally non-abstract. We just have integers and shift operated there. All right, and this this was done by Calderon, so this was his observation that it is possible to reduce such general situation to integer shift system. Well, so the proof goes like that, that we fix P, we want to transfer LP estimates, so we fix also LP function from this abstract space, and we introduce also a bit technical parameter M. And this parameter appears because we want to have everything well defined. So what we do is essentially here we write down the action of those operators on Z. So this is how Z acts on those operators. So a new function phi, which is a function on integers, it is equal just to f at t and x. And we write down this indicator just to make sure that this real function is in small p. Okay? And then for n the capital N and then a small n, which are smaller than the capital N, we can write down these abstract averages. So this is just a definition. So we apply this not at point x but on t and x. And now, since we put 2n here, then we see that this f function is just phi. So this is exactly the same as function phi at point n plus m. And here we discover that this in fact is our operator n, right, on the function phi. All right, so now okay, so this is the identity from the previous slide. So now what we do is we take the fifth power of this identity, then we take the supremum over n, then integral over x, and at the very end, summation in small n. So we use all possible parameters on the left-hand side as well as on the right-hand side. Okay, and now we analyze what happens with the left-hand side. So the left-hand side essentially does not depend on small n, because we can use the fact that t preserves the measure, so we can get rid of this en, right? Because LP norm of the Kaplan operator is the same as the LP norm of the function. Okay, so this gives us n times this integral related to n equal to 0. On the other hand, on the right-hand side, what we do is we make this supremum larger by allowing all capital N's, and also we sum over all small m's. And then we see that this integrand is in fact LP norm of the maximal operator Mn to the fifth power, right? So what we can do is we can get rid of this Mn, because we assume that this estimate holds for this special system, right? So we assume that we have IP boundedness for the corresponding maximal operator. So then we have this constant C, which comes from the maximal estimate for the integer shift system, and we have LP norm to the power p of the function phi. Okay, so here what we do is we come back to the definition. Sorry, but the function phi is just f, t, and x. And there is a restriction that n is between 1 and 2 times capital N. So this is just the definition of phi. And here we once again use the fact that t preserves the measure, so we change the order of summation and integration, and we see that this integration is the same as we will put n equal to 0. So we end up with this sum times LP norm to the fifth power of the function f. All right, so in fact we have 2n times CPs times this LP norm, and now what we should do is we cancel out n's, so we cancel out this n and that n, and we let n to infinity. So then we truly get a supergroup here, and we get that this maximal operator in this abstract situation can be bounded by the LP1 of the function itself. Okay. So here we somehow use the fact that those abstract measure preserving operators they produce some action of Z in the space. All right, so in fact, a similar argument can be used to transfer weak types. So this estimate can be transferred from the integer shift system. The second observation is that this maximum operator on the integer shift system is essentially hard-limited maximum operator on discrete hard-limited maximum operator. In fact, Calderon's transference principle is a much more general tool. It can be used to transfer more general estimates than the maximal estimate. It can be used to transfer variational, oscillation, out-of-jump estimates, and so on. So in some sense, informally, we can say that pointwise convergence for this general setup can be reduced to pointwise convergence in the system. This is not 100% true because pointwise convergence in integer shift system itself is trivial, but what we can transfer is quantitative estimates, okay, which allow us to get pointwise convergence. Also, this transference principle can be used in a more general situation when we consider a system of measure preserving systems, measure preserving transformations. So if we allow to have B transformations, and if we allow that each of them preserves the measure, and also if we assume that they commute each other, and well, the technical assumption is also that they are invertible because we allow polynomials here, so we want to make sure that it makes sense, right? All right. In fact, it can be used also to even more general situations, so we do not need to use the fact that TJ commutes, but then what happens is that this universal system is more complicated. So, for instance, for important step two groups, one can reduce this problem more or less to a discrete hazard. All right, so here is the okay. Maybe I forgot to mention that in this multidimensional situation, the universal system is not Z, but Z. So the corresponding integer shift system is quite similar to the one-dimensional one. So what we have integers, counting measure, and we have a system of measure preserving transformations. So the K transformation is just a shift with respect to K coordinate. Previously I used plus, I used minus in the sense of shift to the left, but it does not change anything. And the corresponding averaging operator is given here. And so here we allow polynomials with integer coefficients, and we assume also that the constant coverage in each of them is equal to 0. All right, so a few words about interpolation. So we have Martinkiewicz interpolation theorem. Probably most of you are familiar with that. So if we have a linear operator, which is of weak type P0, P0, and also weak type P1, P1, then it is of strong type PP for all P strictly between P0 and P1. One need to be more careful with this theorem if you want to interpolate outside the diagonal, interpolating diagonal. All right, so if we are interested in proving highly boundedness, then in fact, since this is one-sided hard-limited maximal operator, in fact, it suffices to consider a larger operator, which is this one, and also here I consider multidimensional situation. So Txn is Euclidean all restricted to lattice points, and I'm averaging around this Euclidean balls, and using Martin-Caggic interpolation theorem, since boundedness on L infinity is trivial, it suffices to prove weak type 1-1. All right, and this is a sketch of this proof. So I want to be very brief. So what we do is we consider a level set, but restricted to a cube, to a large cube, minus n and to the power v. Then from the definition, for each point from this level set, we have this estimate. So to have exactly the estimate coming from that, you need to multiply the lambda and divide by the number of lattice points in the ball. And what happens is that our level set is contained in this sum, with some over all points from this level set. This sum is in fact finite because this here is finite, so this is much easier than the continuous setup. But what happens is that we want to find a disjoint subcollection of those balls, such that if we consider concentric balls with radiuses 3 times larger than the original level set, which is contained in the left-hand side, is contained in this sum. All right, and then, well, it's not hard to construct such a subcollection. And then once we have this, then the number of lattice points in this level set is can be estimated from above and by the measure of this set. So once we know that the measure of this set is more or less of the measure of the original set BJs, and then if we use also this estimate here, then we get this estimate, and finally we use the fact that BJs are disjoint. So here we can increase this summation to the whole set, that we get weak type 1-1 with the constant 3 power t. All right, and at the end we just like m to infinity, and we truly get the estimate for the level. All right, so in fact, using this approach, which is, well, I didn't mention that, but this is a Vitali type argument, covering type argument. So using similar argument, we can prove that partiality to maximal operators defined in a much more general context when we consider measure space with a double measure. Okay, later on I will define this context. But what I want to say is that this argument works in fact in a much more general situation. Also, weak type 1-1 is sharp in the sense that there is no chance for the boundedness on L1. In fact, even something stronger happens. So if you take any L1 function which is non-zero, then the maximal operator on that function is not in L1. So it's no chance for L1 boundedness. And the last remark concerning Berkhoff theorem is that one can proceed in a bit different way, and one can deduce this theorem using Hopf-Danforth-Schwarz maximal theorem, which is stated here. However, this approach is a bit weaker in the sense that here you need to assume that the measure is fine. Okay, and these assumptions which appears here. Okay, so as a P, we take just a Kopman operator. So the first assumption is nothing in this context, and the second assumption that the adjoint of P at function 1 is equal to 1 is equivalent to the fact that P preserves the measure. Okay, so these assumptions are nothing in our context, and then we get type 1. This is a very nice argument, by the way. All right, so in general, so far I considered mainly Berkhoff averages, that is that the function here is just equal to n. but it is quite a natural problem to consider more general averages along polynomial mappings. So here, so here we assume that this polynomial has integer coefficients, and also this is a technical assumption that we assume that the value at 0 is equal to 0. And then what happens is that still we could apply this two-step procedure, and this is not trivial, but it is possible to show that this operator is well, the corresponding maximal operator is bounded on P, but the problem is that here so far no one holds a dense class for which the convergence holds.
Could you repeat last sentence?
Yeah, that it is not trivial to show that the corresponding maximal operator is bounded on P, but it is true. But the problem is that so far no one found a dense class for which this convergence holds. So that's the problem why we cannot apply. Well, we do not know how to apply directly this two-step procedure. So in fact, this problem is somehow motivated also by some considerations in additive combinatorics, and in the 80s, this problem was solved by Bougain's, by Bougain in his famous series of I think 3 papers. So, for instance, for squares, his approach was that he proved maximal operator, but then he also proved that on the tool we have some sort of oscillation estimate. Later on, I will introduce those more advanced tools. But what I would like to tell you at the moment is that maximal operators are very useful, but sometimes they are not enough useful to conclude the pointwise convergence. It's sometimes more convenient to consider more general tools. All right, so summarizing, we have the following theorem. This is a linear situation, which is in fact completely solved today. So the point is that we have this measure preserving system. So we have the transformations, they are invertible, they commute with each other, and we consider such general averages. And then it's possible to show that we have convergence in LP. If P is strictly larger than 1, we have pointwise convergence, and also we have this maximal estimate. So we have a quantitative version of the ergodic theorem. In fact, it's possible to prove here also more advanced estimates, which gives us some information about the speed of convergence. So it's, well, later on I will mention, well, not today, but tomorrow probably I will mention what kind of estimates we have here, which directly implies pointwise convergence. So what is worth to mention here is that we allow sigma finite measures here, which is usually not considered by people in ergodic theory. And also what is important is that this result is sharp in the range of P, in the sense that for P equals 1, this result in such generality does not hold. So for Berkhoff averages, we have pointwise convergence for L1 functions, but for this more general averages, we do not have it. And this is a very, very important and very deep result of Buczolich and Boldin, who disproved pointwise convergence for squares. So just one transformation and Pn equal to n squared. And then it was also disproved for monograms. So n to the power k, k greater or equal to 3 by Lafitore. Okay, the history of this theorem is that for p equal to 1, so if we have just one transformation, this is Berkhoff for pointwise convergence. For convergence in mean, it's von Neumann. Today, the proof which I showed you is essentially works also for for the convergence in L2. And also, if we know that the maximal operator is LP bounded, then convergence in LP is straightforward consequence of pointwise convergence by using terminated convergence theorem. Also, for d equal to 1 and for general polynomial, this is a result of Bourgain from 80s. And we know some quantitative versions of this theorem in the term that we can apply this supremum by some more general things like variational oscillation and Lagrangian semi-norms. All right, and this is my last slide. So in fact, consideration of these operators and the related pointwise convergence was motivated by some problems in additive combinatorics. So there is the following result of Szarek that if we take a subset with positive upper Banach density, which means that we have this inequality, then in such a set, it's possible to find patterns of this type, x plus n squared. All right, so this problem was motivated by the question of Barrow and Furstenberg. And the problem here with this dense class, which I mentioned, that so far no one found this dense class, is that if we take the consecutive terms for the quadratic function, then this tends to infinity. So we strongly use, in the case of Berkhoff theorem, that the difference between two consecutive terms is bounded. All right, and this is what I mentioned about Bourgain's theorem. So he was able to prove the maximal estimate for all p greater than 1, and for L2 he proved also this estimate, which is very well. This is quite weak version of the oscillation estimate. The point here is that he was able to obtain constant which is of this order. So it's small O of the square root of j. This is very important. This is a small O and not the large O. Because the large O is very easy to get just by using maximal estimate. Also, we can estimate this maximal, this supremum by the supremum over O lens, and we can just use the maximal estimate. But then what we get is j, and we take the square root, so we have the square root of j. Here we use better to obtain pointwise convergence. All right, so thank you very much for today.
Thank you very much, Tomasz. Are there any questions? Okay, I don't see any, so thank you both the lecturers for today's lectures, and now we meet for lunch. The session is closed. We'll be back tomorrow at 10. The rounds of downstairs, because the cafeteria will do that. I mean, it doesn't take for me and take it. So.